Hello and welcome back to HeavyBrainSpace. Today I want to talk to you about what we call the heliosphere. This is a region of space that's governed by the solar wind. If you remember from the first episode, the solar wind is comprised of a plasma dragging magnetic fields outward away from the sun. If you haven't seen that first episode, I'll put a link up in the top here and down in the description. Take a few minutes and go check that out real quick and then join us. If you have seen that already or you're coming back from being a first-time viewer, then thank you and I welcome you to HeavyBrainSpace. Let me know what you guys think of this format and let me know if you have any specific questions that you'd like me to answer next time. Cheers. As a space physicist, you learn to look to nature for insight into how the solar system works. Not just looking at light, but at charged particles, electric fields, and magnetic fields. It's not just about what's visible, it's about what's moving and interacting with the things around it. And when you look at all of those things, that's when the real structure of nature seems to come into view. The fields and particle flows interact with one another, and they cause cascades of downstream effects that we work to understand. And nowhere is this more evident than when we look to the solar wind. As it streams outward, it carries the sun's magnetic field with it, shaping a vast and protective bubble around the solar system. And this outflow doesn't just stop at the planets. It keeps going further and further until it can't press anymore. At some distance from the sun, the solar wind meets pressure from the interstellar medium, the space between stars. And it's at this point, or this boundary, that we define the edges of our heliosphere. It's our solar bubble in space. And that's why we care about it. As space physicists, we want to know how the sun is carving out its own space in our galaxy. We want to know how it creates this environment that not only shields us, but protects us and connects us to the broader interstellar medium. From the sun's core to the edges of distant galaxies, the universe is filled with plasma. Charged particles that don't seem to want to sit still. They move, they drag electric fields and magnetic fields, and with this, our sun is no exception. This flow of solar wind defines the boundaries of our heliosphere. It's what tells us how we interact with everything around us. Inside of this bubble, everything is shaped by the solar wind. And that includes not just planets, but fields, dust, and even wave energy that travels outward with that flow of the solar wind. But what's beyond that bubble? What happens when the solar wind stops being dominant? Or in other words, what's happening outside of the influence of our sun? In order to understand how the solar wind interacts with planets and how particles move across the solar system, we need to understand its edges. Where does the sun's influence actually end? How far does its magnetic field reach? And what actually happens at that edge, where the sun's plasma meets the galaxies? That's the question that I keep coming back to. Not just where is this edge, but what does it look like? And how does it interact with the things on the outside of it? In space physics, shape is not cosmetic. It tells you how energy flows, how particles move around. The solar wind expands outward at supersonic speeds, meaning it's faster than the disturbances can travel through it. But supersonic doesn't just mean loud jets or sonic booms. It means that the wind is outrunning its own ability to send signals back upstream. On Earth, the speed of sound depends on altitude. Thicker air at the surface, thinner air higher up. In space, the same idea holds. The speed of information depends on the density, the temperature, and the magnetic structure. When the solar wind slows below this critical speed, it can no longer outrun its own changes. This transition in speeds is what we call the termination shock. And beyond that lies the heliosheath. In the heliosheath, everything gets more turbulent and pressures start to build up. Plasma starts to mix more, fields get twisted and break, and eventually this chaotic zone gives in to the pressure of the interstellar medium. In other words, it's a point where the solar wind pressure no longer dominates. Even though that plasma flow doesn't reverse, wave-like signatures, in fact, can. They're not physical objects reversing their flow. They're wave-like patterns that are showing themselves further upstream. Think about it like a wave passing a point, a ripple in a pond. That ripple, as it comes past you, takes the water and it moves it up and down, maybe forward and backwards as well, and it oscillates more so in place, but it doesn't actually move across the lake. It's the same thing here. We would call that a wave feature, but instead of water, we're looking at plasma in space. And that's a big deal because it means that the solar wind that's beyond the termination shock can still impact regions that are closer in. The final region that we'll talk about here is where all of this chaos and twisting and turning meets the interstellar medium. It's a point that we call the heliopause. It's not a physical wall, it's more of a transition zone. On one side you have the solar wind dominating, and on the other side you have the galactic wind dominating. The heliopause shifts with solar activity. We often cite this distance as 120 AU, or astronomical units. But that's really just an average, because that boundary zone is dynamic. Voyager 1's plasma detector wasn't working when it crossed the heliopause, but its other instruments were still gathering data. That's how we know what kind of environment it had entered. The spacecraft carried a plasma wave subsystem, designed to listen for natural oscillations in the surrounding plasma. These aren't sound waves in the normal sense. There's no air out there. These are oscillations in charged particle density, or plasma waves. By measuring their frequency, we can calculate the plasma density. And that's because the electron plasma frequency is directly related to how densely packed electrons are in the space around the probe. Suddenly, Voyager 1 was detecting frequencies that pointed to a much denser environment, 40 times denser than anything it had seen before. That jump told us it had crossed into something new. The magnetic field direction had shifted too. Not sharply, but enough to suggest that it was no longer aligned with solar origin field lines. Over large scales, the solar magnetic field isn't random. It forms a spiral pattern, shaped by the sun's rotation. It's called the Parker spiral, and it stretches all the way to the edges of the heliosphere. For decades, we pictured the heliosphere to be kind of like a comet, where it's rounded at the front and there's a long trailing tail behind it. And that shape made intuitive sense. The sun moves through the galaxy and its outflow presses against the interstellar medium and it forms a wake behind it. But that picture's beginning to change. Recent data from missions like IBEX and simulations by researchers like Marav Ofer, both of whom I'll link in the description below. These researchers suggest something a little more complex than a wind sock. It might in fact swirl a little more like a flat or deflated croissant. Two lobes, sculpted by the solar magnetic field, extending outward instead of dragging behind. This strange deflated shape isn't just a curiosity, it has implications for how cosmic rays enter our heliosphere, where those particles may be accelerated, and how the sun's influence tapers into the galactic space. It also reframes what we mean by boundaries. Instead of a clean surface or clean edge, we're looking at a complex and variable magnetic interface, something that's shaped by reconnection and turbulence and field-aligned flows. The shape of the heliosphere doesn't just tell us where the sun's influence ends. It lets us know how cosmic rays can actually get to us. Cosmic rays are high-energy particles that are born from wildly violent cosmic events, stuff like supernova. Some of the particles from these explosions can make it into the inner heliosphere, but not all of them. The heliosphere acts as a bit of a filter for us. A long comet-like tail might give cosmic rays an easy path in, but a croissant-shaped heliosphere, one that has lobes that bend and swirl, it might be able to deflect more of them or even trap them. That means that Earth's radiation environment, as well as the other planets, changes depending on the shape of the heliosphere. Magnetic reconnection, where solar and galactic magnetic fields get tangled and twist and break. It plays a big role here. It opens channels for plasma to get in or out. Science doesn't promise certainty. It promises a process, one that gets more reliable over time by constantly challenging itself. For decades, we imagined the heliosphere as one thing, this comet-like model. But then new data came in, from Voyager, from IBEX, and from computer models. And that shape changed. Not because somebody guessed better, but because the evidence showed us differently. That's what we do in space physics, and in science at large. We build models, we test them, and we repeat this process over and over until we have evidence that shows us what reality may be like. The best scientists that I know are not the ones that defend every old idea. They're the ones who are still open to learning and to being proven wrong. And in science, that humility isn't weakness, it's actually fuel for how we make progress. And in cases like this one, it's how we discover the real shape of our heliosphere. Part of what makes doing this, communicating to you all about space physics, so meaningful and so hard is that I really don't want to get it wrong. And it's not just because it's embarrassing, although there is that, but because when you try to explain real science, accuracy matters. And when you're trying to simplify complex topics, it's easy to overstep or make an incorrect statement. That's sort of a new tension that I'm experiencing as a scientist who is also trying to communicate his work. I want to make things understandable, but I don't want to sit here and pretend that I know more than I do. It's not just a fear or being embarrassed or anything, but it's a principle. One of the things that I love about the scientific process is that it's really built for exactly this kind of discomfort. You have an idea and your colleagues, they try to prove you wrong. And if your idea survives, then science as a whole gives you its highest honor, the Nobel Prize. All of the best teachers that I've had in my life had one thing in common. They were comfortable saying, "I don't know." And specifically, as I've come into the field of space physics, a lot of the teachers who do this, they make a very good habit of when they say, "I don't know," they also add, "But let me look into that and I'll get back to you." And the best ones always followed up. And when they did this, they made better scientists and engineers out of everybody in the room. And that's what I'm hoping to foster here with HeavyBrainSpace. It is a learning environment, but it's also a place for us to discuss ideas, to learn together, and to enjoy some heavy music. So if this kind of thing is interesting to you, then stick around and I'll continue to tell you about what it is that I do as a space physicist. Cheers.